Hello everyone, this is Dr. Young, and in this video we're going to start talking about conjugated pi systems. And specifically we're going to take a look at conjugated dienes. So we're going to define them, talk about their stability, and then start to look at how they behave a little bit more, they behave differently than a regular alkene does. So first of all, conjugated, right? We've used these terms before, but it just means when you have 3 or more p orbitals in a row. So it could be 3 p orbitals, it could be 10 p orbitals, it could be 12, any number really. And when you have all those p orbitals in a row, then those pi systems are connected, right? So conjugated just means you have an extended pi system. So more than just a single double bond, whether that double bond is a alkene or a carbonyl or something like that. The types of dienes that we're going to be looking at today are either going to be isolated dienes, which means that those alkenes are not talking to each other, that those pi systems are not connected. We're going to look at the conjugated ones, which is really kind of the crux of this topic. You know, when they're conjugated, they are talking, they are all in a row. And then we also have a weird looking one called allenes. And allenes are a type of cumulated, we don't really need to get into too much detail, but the idea is that you have a carbon that has a double bond on one side and a double bond on another side. So an allene is where you have 2 alkenes and they're sharing a carbon is the idea. So I have a bunch of examples here, right? If I take a look at this first alkene, right? So I've got 1, 2, 3, 4, 5, 6 carbons. If I look at this, I see that I have this carbon is sp2 hybridized. So is this one. So is this one and this one. All 4 of these are sp2 hybridized, which means they all have p orbitals and they're all in a row, right? I've got 1, 2, 3, 4. They're all in a row, which means this becomes one whole pi system. These are connected, or in other words, they are conjugated because it goes double bond, single bond, double bond. So this would be an example of a conjugated diene. Compare this to the one on the right. If I look at the one on the right here, I do have an alkene over here, check, but I have an alkene over here also, but they're too far apart, right? So if I take a look at these, yes, these carbons are sp2 hybridized, right? This one and this one, as are these 2 over here, right? They both have 1 p orbital. However, this carbon in the middle is sp3 hybridized, which means it does not have any p orbitals left over. They've all been hybridized. And so there is no a p orbital to participate in a pi system. So this would be considered an isolated diene. Because these 2 pi bonds are isolated. There is one over here and there's one over here, but they're not connected. I can't delocalize them and draw resonance structures, etc. So they're isolated from one another versus conjugated. If I look at this other one down here, same sort of story. I have double bonds over on the left and on the right. Way too many sp3 carbons in the middle, so these would be isolated. They're not conjugated, they're not connected to each other. Versus this one, I do have the alkenes right next to each other. Again, all 4 of these are all sp2 hybridized. So they all have a pi system, so this would be conjugated. Right? Because they're, again, double, single, double. So this would form one whole pi system, and we'll take a look at what those orbitals look like in a sec. And then lastly, as you might have guessed, this is that weird one where I have a double bond connected directly to a carbon, and it has another double bond on it, so that would be an example of an allene. And those are relatively unstable. You can find them. I mean, we'll see some examples of them, but they're relatively unstable, not found too often in nature, for example. But that's an allene. And I put the carbon there in the middle. It can look kind of funky if you don't put the carbon in the middle, because then you'd just be doing a double bond and then a double bond. But sometimes I just like a really long double bond there. But that would be an example of an allene. So you should be able to look at the 4 down below, right, and say right off the bat, are these isolated, are these conjugated, or are these allenes? And so for this one down here, it doesn't matter if it's a ring or a straight chain thing. I know sometimes people freak out when they see rings. All my examples up there were straight chain, but you'd have the same sort of logics here, right? So I in this case, I have an alkene and an alkene, but they're being separated, so that's isolated. That'd be an isolated diene. Versus here we have our conjugated one, right? Those are right next to each other. Again, double, single, double. Same thing here, right? These are right next to each other. So I have 4 atoms in a row that are all sp3 hybridized. Oops. That one's conjugated. This one. Oh, yeah, and that one is too. Sorry, I don't know why that got erased. So those are both conjugated. And then lastly, this one over here would be isolated, right? Because I have, once again, I have sp3 carbons in between the two of them, isolating them from one another. They're no longer talking, we don't have those orbitals being overlapped. Now what we see here, let me go to the next slide. What we see here is that the conjugation, having a conjugated diene is slightly more stable than having isolated dienes. So here's some heat of hydrogenation data. We often use heat of hydrogenation data to get a relative sense of how stable molecules are compared to one another. And so we just literally are doing catalytic hydrogenation, right? So you learn this reaction here where we can take this alkene and hydrogenate it down to the alkane. And when you do that, it releases about 30 kilocalories per mole of that stuff that you reduce, that you hydrogenate. And that's what this data over here on this chart is kind of saying here, that if I start with this alkene and I hydrogenate it, it releases 30 kcals of energy. That's what that difference is. All right, so if I go down to the pentane to the pentane. Now, as a comparison here, I have, as you might expect, the more pi bonds you have, the less stable something gets, right? So we keep going up and up and up and up in energy with more pi bonds that we have, right? Remember that pi bonds are weaker than sigma bonds. They're less stable than sigma bonds. They're higher in energy. And so if you look up something here, we have our alkyne. Alkynes have 2 pi bonds. So do allenes. And these two are about the same energy as each other. They're about 70 kcals in energy higher than if you hydrogenated them back down to the pentane. But if you look at what's kind of interesting here, if you look at our 2 dienes, the isolated one up above is slightly higher in energy than the conjugated one. So there is a thermodynamic drive to have your dienes conjugated versus isolated. And so sometimes there's certain types of reactions, radical reaction stuff, that can actually get your alkenes to kind of move over and to become conjugated. And that's, again, just because they're slightly lower in energy. Why are they slightly lower in energy? Again, it's because we can spread out electrons into that pi system, drawing resonance structures. So let me show you kind of what we're talking about. If I take a look at this, right, so here's just a diene, a butadiene. I got this image from LibreTexts. So if I draw the p orbitals here, right, so if I draw one p orbital, here's another p orbital. I'll just do all the reds at once and all the blues at once. Right, so I've got all of these p orbitals. These are the ones that are participating in the pi bonds, right? And so the idea here is that if they're all lined up, right, they're all sp2 hybridized, so they all have 1 p orbital left over, that they can blend constructively to join all of those p orbitals together to have a larger pi system. So it's not like you just have one alkene and then you have another alkene. It all blends together to be one big stack of electrons on top of the molecule and one big stack of electron density on the bottom of the molecule, right? So you have electron density on top and below, like a normal alkene, only it extends out. And it's not 2 separate blobs, it's all one smooth blob. It's like you're spreading out jelly across a piece of toast, right? It's all spread out over the entire molecule. And that's going to lower the energy of the molecule just a little bit. We'll see that if something becomes aromatic, which will be later on, that'll reduce energy a ton because there's a lot more resonance. But if I look at these, right, I can draw resonance structures. So if I have this molecule, right, if I have this 1,3-butadiene, I can draw a resonance structure where, say, I have these electrons move to the left and, move to the right and kick out over here to give me this. Or instead of moving them right, I could have moved them left, would have given me an equivalent, but different resonance structure where I move the negative to the right, to the left versus the right. So I have these delocalized electrons, right? I can draw them using these resonance contributors. That's kind of what we're trying to say, is that these electrons can be spread out, they're conjugated. We're able to delocalize those electrons. Now, what we're going to see in this example, right, is that I definitely have a major contributor versus much more minor contributors. And that's just because, right, again, nature favors neutral things. So probably, and most of the time, having no charge is better than having charge. And so it's not like these ones on the right are going to be particularly major contributors, because you've got a carb anion, which is very unstable, and you have primary carbocations, which are also very unstable. They're not insignificant. They're just significant enough to lower the energy a little bit, which is what we saw in that previous slide. Now, why do we care about identifying these as being conjugated dienes? And the reason why is because they behave a little bit differently, right? So before we learned that, oh, well, if I have a single alkene and I add Br2, I'm going to get something where the bromines add, and they do this anti-addition that tends to follow the sort of Markovnikov type reactivity. So just wherever the alkene is, that's where you have the two bromines. Now, if you have just one equivalent of Br2 here, what you end up getting is a kind of odd at first looking molecule. So you do add two bromines, but they're not right next to each other, and it looks like the double bond moves. And so what I want to talk about in the next video is how do these conjugated dienes react? And we'll talk about 1,2 versus 1,4 additions in thermodynamic versus kinetic conditions. So that's going to be our next video. So hopefully after this video, you feel a little bit better about the difference between an isolated diene, a conjugated diene, and an alene. You should know that the conjugated dienes are a little bit more stable than isolated dienes, and that's because their pi systems overlap, so we can delocalize those electrons. And now in the next video, like I said, we are going to talk about how do conjugated dienes react differently. What's kind of different about them? Why do they behave a little oddly? All right, so study up and good luck.